In this tutorial, we're going to go over setting up your Fusion 360 model to create joints that will be used for a URDF file export that we can bring into IsaacSim to do physics simulation. It'll let us do this type of robotic simulation where the robot can bounce into hit objects, and then when it hits a higher mass object, it bounces off. So we're going to start off with a pre-configured robot where we have the model but without any joints. We're going to make sure that our main body is pinned. So we right-click and pin, and we want to make sure that it is grounded parent and nothing else has a grounded parent. We're going to hide all of the parts except for the root. We're going to go to Assemble, Joint Origin, and we're going to select where all of the joints will be once we have the final robot. Let's continue this. For good practice, after we've created all the joint origins, we're going to start renaming them. So for example, this one will be spinning top, and we'll continue. With everything named, we're going to start creating our joints. Press J. J will open up the joint dialog. We'll start with the spinning top. We have component 1, which is going to be the child, and component 2, which is going to be the parent. So for component 1, we'll select the location where we would like the joint. And for component 2, we're going to go to the joint origins, and we're going to select our joint origin for spinning top. We will then click on motion, and we want to make sure that the revolute joint type instead of rivet, rigid, and our rotation is correct. If we click preview motion, we'll see it moving. Let's click OK. It'll create the joint, and we'll name this spinning top. Let's repeat that process for the rest of them. Now that we've selected all of our joints, we can start to animate them. If I right-click, animate joint, we'll see that it rotates forwards, as if the car was going to move forwards. That's great. I'll press escape. If I select the other back wheel, and I right-click and animate joint, see it's moving in the opposite direction. This is also visible by the flag facing forward and the flag facing back. What this means is if we were to drive this joint, going forward would be positive. If I was to drive this joint, going forward is negative. So we need to flip this joint. First, I'll rename my joints to make this easier to follow. To flip the joint, since this one is going in the correct direction, we're going to check that this is the back right wheel. Back right wheel, origin, right click, edit joint origin, click flip. Now that we flipped it, the joint origin is aligned, but our wheel has rotated as well. So our wheel flipped on this side. Now we will go to back right wheel, right click, edit joint, and we will uncheck this flip, click OK, and now our wheel will rotate in the correct direction. So let's try that process again. We're going to select on the front right wheel. So right click, edit joint, front right wheel, flip it. You'll see that it actually flipped the whole object. So we'll go to front right wheel here, edit joint, and we'll uncheck that flip. Okay. And now all of our joints are facing in the same direction. Now it's time to export as a URDF. We'll go to the utilities, click add-ins, scripts and add-ins, and we're going to press this green button to navigate to where our descriptor file is. If you don't see this, it's because we still have to add the plugin. Click the green checkbox, the plus. A normal dialog will show up, and we're just going to click our location that we've extracted our files to, and this descriptor folder will show up. We're going to select the code, and you'll get a new dialog or menu item here. Now we'll press run, and you'll have the option to set your save directory. So set save directory, and you can pick any location you want. I'm just going to click on this main folder. Now we want to save our mesh. We want to convert the mesh to an OBJ file because it'll improve the scaling capabilities that we have. And we're going to make sure that our docking minutes are in centimeters and our target unit is in meters. Joint component should be child. If you remember originally, when we selected the joint, we selected the wheel first and then the base origin. The wheel is our child and the base is the parent. It's not necessary, but we can click preview links and we'll make sure that we see these parent-child relationships. Now that we're ready, we will click generate. And depending on the complexity of your model, it'll flash and then show up again. Now open up the File Explorer and check that in the folder that you saved it to, we can see car description. Car description is because my file name is car, and then it'll always add this description tag to it. If you double click, you should have a folder. A meshes folder will be OBJs and STLs. The OBJs are because we converted to an OBJ. And we have a URDF, and the URDF file should be more than 1 kilobyte, and you should have some data associated with it. If you open this URDF file, you should see a couple of drop downs, such as main body, the link name, spinning, back wheel, etc. And we should have all of our joints. So these are the joint names. It's okay if your link name doesn't match your joint name. What's important is that the joint name will end up matching the actual joint itself. And in each joint, it'll talk about the parent being main body and the child being spinning. Same thing with back left. We have the parent as main body and the child as the back left wheel. Okay, now we're ready to take this file into IsaacSim. Now we're going to take our Fusion 360 URDF file that we had exported and processed and open up IsaacSim, go to Isaac Utils Workflows URDF Importer. Depending on the case, you're going to have different desires for these positions or these buttons, but we're going to remove fixed base link so that the position of the robot can change. We don't need to worry about damping and joint strengths because we're going to change them later. We don't need to use convex decomposition. Typically we would, but we're going to change that manually anyway. We don't want self-collision currently because our objects are going to hit into each other. We don't need collisions from visuals because our URDF exporter already processed collision meshes. And we're going to create a physics scene. Finally, we will click this button to open up the window and select our URDF file. Navigate to the folder where we saved it. I saved it into demo URDF. We'll click on it. We should have two folders, meshes and URDF. Click on URDF and then select the file. You should see all of your joints show up in the joint drop-down list right next to it. Now select import. It's going to ask you if it's okay to save the URDF file path USD. We'll click yes. And our robot has imported. So we can close this window. I'll click on the car. I'll press F to zoom into the car. The car is pretty small, but that's because we used centimeters when we were making this in Fusion. So it is a pretty small ant weight type robot. If we select the object and you don't have any of these visualizations, click on the eye, show by type, physics, and you can show joints. And under colliders, you can show no colliders or the selected colliders. If we were to play this, our robot's going to fall because there's gravity and we don't have a ground plane. We can create a ground plane by right-clicking on World, create physics ground plane. Based on our robot location, it's intersecting with the ground plane. So I'll select the car, use the move command or press W and move the car up. Okay, now when we press play, the car falls onto the ground. So we know physics is working. Now let's select each of these meshes So I'm going to select on the collisions. And under the Properties panel, go to Physics, Collider, and I'm going to change from Convex Hull to STF Mesh. Now we get a much higher resolution and better representation of what the mesh looks like. We can make sure that it still works by pressing play. Great. Our next step is going to be driving the robot. We are going to open up our main body and see all of the physics revolute joints. These are the joints that were defined in Fusion, and we imported here. This is automatically created for us, and under the lower and upper limit, because these are wheels in Fusion, we hadn't set any limits. If you do, then this would say the minimum and maximum degrees it can rotate. We want drive to say angular. We'll modify the force later if needed, but because we're going to use target velocity, we're going to remove the stiffness and just add damping. I'll put 500 here, and I'm going to do that for the rest of these files. Remove this and set damping to 500 and continue along. I've gone through each of these and we now have 0 stiffness, 500 damping. So let's start with the spinning top because that's the easiest to recognize. We have damping at 500. The target velocity, let's say 50. If you use the tooltip over target velocity, you can see for this angular drive, we have degrees a second. So our target is 50 degrees per second. If I press play, we will start seeing that this spins. We know that it's interactive physics because if I hold shift, I can use the mouse drag and control, and this will move it around. And we can try to stop this spinning blade, but we have a pretty strong motor or joint. So let's stop that. This should start working. So now we have target velocity. We can make the blade spin quite a bit faster. So we'll triple that speed and we get this moving. If for some reason velocity here is not matching the target, then you have some problem, and double check that your stiffness is 0 and your damping is 0 and your damping is above 0. So let's end that. We do want to make sure that we have pretty good collisions. In order to do that, we want to check the physics scene and enable the CCD, which is continuous collision detection. This will help make sure that when an object gets hit, it doesn't penetrate more than it should. We also want to bump up some of the minimum requirements for the iteration counts to ensure that our simulation is working well. Okay, at this point, we're going to try to get the robot to drive. So select a back left wheel and a back right wheel. So the back left wheel, we will go down to target velocity, and we'll say we want this target velocity to be 150. And the back right wheel, target velocity, 150. Now when we press play, the wheels will start to rotate, and depending on how you designed your wheel, your car will go more or less straight or fast. We can apply physics materials to change the friction. For now, let's stop this, and let's just add some front wheel drive as well. So I'll take the front right, I'll make target velocity 150, and front left wheel, target velocity 150. Because we add these little grips, we should get a little bit better traction here. Great. Now we have a car that moves. Let's stop that, and let's make sure that we can interact with other elements in the scene. So to make sure that we have CCD and collisions enabled, we're going to make a new object under World, right-click, create mesh, and we want to create a cylinder. The cylinder is being created in meters, so we'll click Scale, uniformly scale it down. And just from the shadow, we can tell where it is. We'll move the cylinder over here. In order to make the cylinder interactive with the scene, because right now, if we press play, the cylinder has no relationship to the car or the physics simulation. We're going to scale our object to the size we want. So I'll press R or the scale tool. I'll scale this in so it's a little bit thinner. And now I'm going to right click on the cylinder and I'm going to do add physics rigid body with collider preset. And you'll see these green lines show up, which is the collider. Open up the physics dropdown, scroll through, enable our CCD for this object, open up the collider, and again, we'll want to click STF mesh. Now, if we press play, we can see that the cylinder does drop down. And we'll look at our spinning object, which will get closer to the cylinder and then knocks over the cylinder. And it continues to move.